Hello, this is Mr. White. This video is on concavity and inflection points. Here are the three exercises for today. All right, before we get into that first one, let's review real quickly the concept of concavity. And the good news is that there's a certain amount of intuition that will serve us well here. When we're feeling down, we tend to be frowning. And so concave down intervals of a graph are what I'll also refer to as frowning intervals of a graph. And again, concave down, frowning. And furthermore, when we're feeling down and we're frowning, we tend to feel negative. And it turns out that those are the intervals of the graph where the second derivative is negative. So it all agrees, concave down, frowning, negative. And on the other hand, when we're feeling up, concave up, we are smiling. And the second derivative is positive for concave up intervals of a graph. Another way that one should be able to look at concavity is whether a graph is above or below its own tangent line. So for this graph that we see here, when I bring the tangent line onto the screen, we see that for this frowning interval of the graph, we see that the blue graph is below the red tangent line. Whereas for the smiling portion, the smiling interval, the blue graph is above the red tangent line. And notice that the point of inflection is where the graph changes from frowning to smiling or vice versa. And if I turn the trace feature on in GeoGebra, I can get a pretty cool image on the screen when I trace through all those tangent lines. Okay, but back to our first exercise. Let's determine the open intervals on which this graph is concave up or concave down. Let's start by identifying the discontinuities. In this case, the vertical asymptotes. So there are two discontinuities. That's where concavity, in addition to inflection points, discontinuities are where concavity might change. And let's look at where else let's look for those inflection points. So starting with this first stretch of graph right here, is it smiling or frowning? Well, it starts off smiling, right? Here's a little smiling portion, and then at some point in there, it starts frowning. And unlike extrema, where it's fairly easy to definitively say with pretty good certainty that there's our local maximum right there, sometimes it's a little harder to identify visually, graphically. It's a little harder to identify exactly where a graph stopped smiling and started frowning. So we just do our best there. I'm going to say it looks to be right around there. So I'll bring a line over here to mark that off. And let's look at the middle portion of the graph. Do we see an inflection point there along this stretch? Well, it starts off frowning, and then it finishes up smiling. And it's a little easier there, or at least it's a little more convincing to say that that probably occurs right at the origin. So I'll put a line there to signify that we've got an inflection point right there. And how about that last portion? Well, that does not have an inflection point. It's frowning the whole way. And granted, it's a little bit hard to tell. If we were to just zoom in on that or zoom in on this right here, it's a little hard to tell whether it's frowning or just linear. But looking at the whole thing, we'll agree that that is frowning the entire way. So our intervals of concave up and concave down. Let's put some numbers on this graph, and we'll say that we'll assume that these are counting off by 1, 2, 3, 4, 5, etc. Same on the y direction. So we'll say that this is -4, this is -2, this is 0, this is +2. And concave up, we are smiling along here. And if we were to assume that the graph continues to be concave up all the way to -infinity, we would put -infinity all the way up to -4. That's not the type of thing that I or the AP exam is going to try to nail you on. Where's our next concave up? Looks like this is our next concave up, our next smiling stretch. So that would be from 0 to 2. And that's it for concave up, right? So let's take a look at concave down. We now have concave down from -4 to -2. From -2 to 0, and again, remember these are all x values that I'm writing here. These are all x intervals. And then from 2 all the way to infinity. And again, we're going to assume that it continues that way all the way to infinity. Whoops. Yeah, that was right, wasn't it? Yeah, 2 to infinity. And those are what we're asked for, the open intervals on which the graph is concave up or concave down. So put a box around it. We're done with this one. So let's go on to the next one. Okay, here we are to find the points of inflection and discuss the concavity of the graph of the function. And by discuss the concavity, that means give intervals of concave up and concave down. So we know that since we're dealing with inflection and concavity, that we're going to need to find the second derivative. And your first instinct may be to do the product rule, right? Because we have a product of two functions of x. But what would be easier? How about we go ahead and distribute that x cubed? Let's distribute that and get x to the 4th minus 4x cubed. And then we'll take our derivatives. So here, f prime of x, if I derive x to the 4th, I get 4x cubed. And if I derive minus 4x cubed, I get minus 12x squared. If I wanted to find extrema and critical numbers, I would go ahead and work with f prime. But here, I'm interested in inflection and concavity, so I'll derive again, and I'll get 12x squared minus 24x. And since this is f prime that I'm wanting to work with and that I'm going to next set equal to 0, let's go ahead and factor that. Let's factor out the greatest common factor, which in this case is going to be 12x. So 12x on the outside, that means that inside those parentheses I need an x, because 12x times x will give me the 12x squared. And I need a minus 2, because 12x times negative 2 will give me the minus 24x. That is what I will now set equal to 0, given the task that we were told to perform here. That's what I'll set equal to 0, or undefined. And we'll go ahead and solve for that. So the 12x there, that will give me x equals 0. And the x minus 2 there, that will give me x equals 2. And those both are in the domain of the function, the original function. But let's remember, we're not calling these critical numbers. We'll just call these possible inflection points. Possible inflection points, not a more special name for it than that. Okay? So at this point, it's starting to feel a lot like the old first derivative test. And in fact, we'll be creating a table very similar to the first derivative test. The main difference, of course, is that instead of the sign of f prime, I have f double prime here appropriately. However, I have to tell you, this is a point of confusion for students every year. Even though we're doing basically the first derivative test, but using the second derivative instead, this is not the second derivative test. Second derivative test is just around the corner, but this is not it. So every year, students want to call this the second derivative test. It's not. We'll save that for another day. It just feels a lot like that first derivative test. So let's consider our number line, where here's 0, here's 2, negative infinity, and infinity over here. And our first interval will be from negative infinity to 0, and then from 0 to 2, and then from 2 to infinity. We'll still do those intervals. We'll still pick test values just like the first derivative test. And this time, of course, instead of looking at f prime, we'll look at f double prime. And f double prime happens to still be on the screen. F double prime of x. Here is our most useful form of f double prime of x. And if I plug in our first test value of negative 1, negative 1, negative 1, negative 1, I'm going to get a negative 12 times negative 1 times another negative. Negative 1 minus 2 is also negative. So that means my sign of f double prime is negative times negative, or positive. And same caution applies that I issued with the first derivative test. Don't just assume that we're always going to get alternating signs here. Don't assume off the bat it'll be positive, negative, positive. Many times it will, but sometimes it won't. So let's plug in our second test value, f of 1. And over here we get 12 times 1 times quantity 1 minus 2. And we get, oops, I still have the negatives there, but I get positive this time times something that's still negative. So this did switch signs, negative there. And finally, plug in our last test value of 3, 12 times 3 times 3 minus 2, positive, positive. So it did alternate. We just had to check and make sure of that. So remember the conclusions here this time don't have to do with increasing and decreasing anymore. We weren't dealing with f prime, we're dealing with f double prime. So a positive now means not increasing, but concave up. And a negative means concave down, and then concave up again. And since we were to give the intervals of concave up and concave down, I'll just complete the sentence here. Concave up from negative infinity to 0, concave down on 0 to 2, concave up on 2 to infinity. So that was part of what we were asked to do, discussing the intervals of concavity. And we're also asked to find the inflection points. And since these second derivatives did indeed change sign, that means that we really do have inflection points at 0 and 2. I should point out that if these did not change sign, like let's say for instance this was negative and this also ended up being negative, in that case this value of 2 right here would not be considered an inflection point. Remember we called it earlier. Earlier we called it a possible inflection point, and to verify that it truly is an inflection point, you have to see that the f double prime changed sign. And in this case it did. So we have inflection points then. We have inflection points at, we had a value of 0, an x value of 0. And we also had the x value of 2. We did verify those are both actual inflection points. And if I bring the original function back onto the screen, I see that f of 0 equals 0 times negative 4. That'll give us a 0. And f of 2 will give us 2 cubed, or 8, times 2 minus 4, negative 2. That's going to give us negative 16. Those are our two inflection points. And let's take a look at a graphing calculator verification of our answer. Let's scroll down a little here and bring this up. So on the graphing calculator, we indeed see that the graph was concave up. It was smiling all the way up to the origin. And then it started frowning between x equals 0 and x equals 2, just like we said it would. And then it went back to smiling from 2 on to infinity. And we see the inflection points there as well. All right, let's go on to our last exercise. Okay, same task here, this time involving a trig function. Let's see if that makes things any more difficult. Let's start with our second derivative, right? Which of course requires that we start with the first derivative, really. Minus 4 sine x. We derive it again. G double prime is going to equal 2 minus 4 cosine x. and we'll set that equal to 0 or undefined. And thankfully, good news for us, that turns out to be a pretty easy one to solve. I'm not going to get undefined because cosine of x is never undefined. You can plug any real number into cosine x and get a real output. But if I rearrange this equation algebraically, I would get cosine of x equals 1/2. And I know that that only occurs at least within this interval. I should have pointed that out. We're dealing with the interval from 0 to 2 pi. So within that interval, we're going to get cosine of x equals 1/2 at pi over 3 or 5 pi over 3. We're talking about the steep special triangle in the first and the fourth quadrant, pi over 3 and 5 pi over 3. So those are called our possible inflection points. Possible inflection points. And let's go ahead and make our interval. Now again, we are working on the interval from 0 to 2 pi, so we're not going to go between negative infinity and infinity for our number line. We're just going to go from 0 to pi, and we know we have a pi over 3 and a 5 pi over 3. So here's our table. I've already just filled in those intervals there. We need a test value next. So I put, trying to stick to special angles, we'll put pi over 6. How about just pi? And how about 11 pi over 6? And again, I probably mentioned in class ways that we could tackle this without actually picking specific test values, but I'll leave that for class time. And now we want the sine of f double prime. And I've still got that visible up here on the screen. What will probably make my job a little bit easier is to factor that. I didn't do that before. So let's say that that equals 2 times 1 minus 2 cosine x. We'll do that. So when I plug in my first test value of pi over 6, I know that the cosine of pi over 6 is going to be root 3 over 2. So when I take root 3 over 2 and multiply it times 2, all of this is going to be equal to root 3. And we know that root 3 is about 1.7 something, something, something. Let me get this number line out of the way. So if I've got 1 minus the square root of 3, 1.7 something, 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 I know that this is negative. So what I'm trying to model for you here is that, again, just being able to do these calculations relatively quickly. I know it comes more easily to some students than others, but please avoid the temptation of using the calculator here. We should strive to do this without a calculator. Okay, next test value of pi. That's a nice easy one. Cosine of pi is going to be negative 1, right? So if I've got 1 minus 2 times negative 1, that's going to be plus 2. I've got 1 plus 2. That means that this is all 3. This is all positive times our positive 2. Okay? And finally, 11 pi over 6. Well, keep in mind where that is on the unit circle. This is 11 pi over 6. Our first test value there, pi over 6, was its mirror image across the x-axis. So pi over 6 and 11 pi over 6 have the same adjacent over hypotenuse. They have the same cosine. So whatever I got, whatever conclusion I drew for pi over 6, I'm going to get the same conclusion for 11 pi over 6. That means I have a negative right there. Okay, I know I'm going through this quickly. Of course, pause if you need to let that soak in. Similar to the last exercise, we know the conclusion has to do with f double prime, so we know that this is not decreasing, it's concave down, whereas this is concave up, followed by another concave down. Okay, and there I've completed the sentence. Put a box around that. That's the discussion of the concavity. And as far as points of inflection go, since the second derivative did change signs, we have verified that those possible point of inflections are actually points of inflections. So we'll go ahead and document those as being at, see, pi over 3 was one of the values, and then 5 pi over 3 was another value. And if I scroll down and plug in those two x values, I can get my y values. So pi squared over 9 plus 2, and then 25 pi squared over 9 plus 2. And those are my points of inflection. If I plug those into a calculator and get some decimal approximations, I get those values. And if I were to continue with the calculator and try to get a graphical verification there, I see that it does agree with the answers I was getting, or that we got here. So again, notice that it's a little bit harder to tell graphically that this is frowning, but we kind of can make out, or we can at least believe it's frowning here, and that it smiles here, and then it turns to frowning here. And we see here, again, another case where the calculator alone isn't going to do the trick for us. We really needed those analytic techniques to determine where the inflection points were.